So, thanks Sinead for that. So my name is Ciaran O'Leary. I'm with i3PT. And firstly, a bit of background to i3PT. We are a leading assigned certified company in Ireland. We are working on some of the most prestigious projects in the country. Everything we do is about delivering better buildings and an improved culture on building sites. So what we do is as shown in the slide. Briefly, we do things like quality management, query management, lead and BREEAM, assigned certifier and design certifier, to name a few. And we do this with our own in-house internationally recognized software called Search Central. As we like to say, it's a single source of truth for your project. We've about 60 staff and we've about 8 or 9 programmers working on Search Central on a daily basis. So today's presentation will be as follows. We'll start by looking at where Part L comes from, including cost optimality, and where the 2 Part Ls are applicable. We'll then look at thermal bridges and air permeability and how the code deals with them, and some examples of what we at i3PT look for in order to show compliance. For the presentation, I wanted to keep a narrow focus so that, as I know that most people will only take away 2 or 3 things with them. Hopefully, you will take away the understanding that thermal bridges are very important, air permeability is very important, and that Part L is based on good scientific and economic facts. At the end of the presentation, we'll also have some time for questions if anybody has any. So today, the main question to answer is, how do you show compliance with Part L and why? So Part L is the TGD which aims to ensure all constructions are built so that they are nearly zero energy buildings. An NZEB is a reference building which consumes nearly zero energy in heating, cooling, hot water production, and lighting. And the EU has basically defined an NZEB as a building which is the cost often with construction. I think it's important that we understand that this, as I've personally heard, that perhaps we should build different levels of energy efficiency buildings for the market to BER rated building. The fact is, what we are doing is making the most cost-effective building for that person based on the complete life cycle of the building. So Part L is based on EN 15459. And in that, we bring all future costs back to the net present value for various scenarios. And we compare these to see which is the cheapest. The reference building that is assessed is a hypothetical building, which has been determined for a specific building type. In Ireland, we have a database of building topographies on a system called Tabula. For example, the average size of an office block in Ireland could be determined, and this will be the reference building for the Irish cost optimal studies. An example of net present value equation is shown here, and I'll briefly explain the various parts of it now. IN is the initial investment, for example, the cost of installing installation plus the cost of the materials. Z here is any maintenance or repair costs associated with the product to be installed, or would be any residual value of the component at the end of the investment period. An example may be the boiler may have scrap value at the end of its lifespan. E new is the energy consumed or saved by the building by applying the component. D would be any costs associated with demolition or disposal of the component at the end of its lifespan, i.e. pulling out the boiler and the cost of a truck to drive it down the road to the scrapyard. A sinking fund is the value of any additional investment required to replace the component in the future, i.e. you put away €10 a month from now, so that in 20 years, this €10 per month will cover the cost of replacing the boiler. And CO2 is the cost of carbon associated with the component's energy saving or consumption. Here we see examples of various scenarios. So just to look at this briefly, we can see that each scenario is slightly different. The only difference between scenario 1 and 2 is that the window U value is a little bit better in scenario 2. Scenario 3 is like scenario 1, but with a different heating system. And you can keep doing this until you've covered all possible scenarios for the building. And just for your information, when I worked on this for the Greek government, we had over 1 million scenarios for our reference building. So what this gives us is many dots on a graph like that shown. Each dot represents an individual scenario. The lowest dot is the cost optimum, and this dot will generate backstop values for things like the U value, G values, if you like, coefficient of performances and the like. And this is what gets used in Part L. So the two Part Ls are Part L 2019, dwellings, and Part L 2017, buildings other than dwellings. And there are two reasons to apply the codes correctly. These are to ensure compliance with building regulations and to save your client's construction and running costs. Part L 2019, dwellings apply to houses, apartment blocks, student accommodations and the like. It applies to the individual unit, so don't use a BER with averages of all the apartments together. Briefly, is not applicable where planning approval has been applied for on or before the 31st of October 2019, and substantial work has been completed by the 31st of October 2020. Substantial work means the structure or external walls have been completed. Part L 2017, buildings other than dwellings, apply to retail, hotels, apart hotels, office blocks, and the like. It does not apply to specialist process requirements, i.e. cooling plant and data centers. It is not applicable where planning approval has been applied for on or before the 31st of December 2018, and where substantial work has been completed by the 1st of January 2020. So just to look at terminal bridges specifically, how important are they? It's a good starting point. Well, I have heard that terminal bridges can result in 30% of heat losses. I've also come across a report by the EPBD, which indicated you could achieve a 15% reduction in heating costs if terminal bridges are calculated as opposed to using brochure values. But in any case, what you can say for sure is that terminal bridges are significant. Part L 1332 says that all key junctions should be assessed. But what is a key junction? A key junction could be where terminal bridges pose a risk of surface or interstitial condensation. In Part L 2017, the reference building, the junctions identified were as shown below here, the 7 shown. But you're probably not building the reference building, and therefore you may have additional terminal bridges. So in essence, any terminal bridge which could cause condensation should be addressed. And Part L 1332 gives 3 ways of doing this. And you probably can look at that yourselves because we wouldn't have time to go through each one here on within the hour. So in order to show compliance, we need to have a golden thread between concept and completion. Where are the key terminal bridge values in meet deep? Where are the 2D representations of these terminal bridge values? Where are the for construction details that translate these 2D representations into construction drawings? And where are the pictures from site inspections showing key junctions constructed? You can see some examples of terminal bridges. You can see on the left hand picture, there's a overhang. You can see in the soffit there's a column. You can also, it's a bit hard to see, but you can see that you might be able to see that there's some lights countersunk into that soffit, and these would also be terminal bridges possibly. So you've got the balcony connections and you've got the roof parapet details. These are all details which may need to be looked at in designs which need to comply with the latest Part Ls. For air permeability, the following represents a reasonable approach to design and construction of buildings. That is to A, identify the primary air barrier elements at the early design stage, develop appropriate details and performance specifications, and provide on-site inspection regime and related quality control measures. Key wording here is develop appropriate details and provide on-site inspections. So for a particular project, you may need to ask yourself, where is the air tightness layer? Does it follow the thermal layer? For example, is my bin store parking within the air tightness layer? What is the method being applied to seal for penetrations? That is, for the dry rise or for the gas connection. How are we testing the building? For example, do you leave the louvers in the bin store open, or do you need an airtight door in the bin store? Is it a large and complex building? Again, like for thermal bridges, we aim to have a golden thread between concept and completion of all details. Where is the document drawings identifying the primary air barrier at early design stage? Where are for construction details and air tightness specifications that translate these early design stage representations into construction drawings? And where are the pictures from site inspections showing the details constructed? You might notice the passive host methodology in the images shown here. So as an example, let's look at a situation where we have a bin store in the building. ATTMA TSL2 121 says air leakage is the uncontrolled flow of air through gaps and cracks in the fabric of a building. This is not to be confused with ventilation. So are the louvers in my bin store part of the ventilation strategy for the building, or for ventilation of the bin store due to TGD Part B 1412? Probably due to hygiene requirements, they're not part of the ventilation strategy. Therefore, the air tightness layer is probably at the door between the bin store and the main building. For air testing, the door between the bin store and the main building probably needs to be closed and the louvers untouched. And therefore, you might need to consider this door's quality for air tightness. And finally, how does this affect your neap or deep and your thermal inflow? So, in summary, thermal bridges should be assessed on their risk to cause condensation. Air permeability needs to be designed for, that is, a strategy, drawings and specifications. A golden thread between design and construction needs to be produced, and you should start the above processes early. Thank you very much, and I'll take any questions now.